everyone! Welcome to our project on uncertainty estimation for a robust SLAM using Bayesian deep learning. I'm Carla, and along with CFAT and our advisor, Dr. Dara, we are so excited to be showing you our work. So today we're going to be going over our motivation for the project, what SLAM is, some real-world applications, our method, everything that we're using to do this, our environment, and what we're currently doing and will hope to do in the future. Okay, what are we doing? So basically, if a robot is learning how to do something in an environment, we want to be able to quantify its uncertainty. So we want to, if a robot is figuring out, is that a tumor in your brain? How sure are you? We want to be able to put an uncertainty estimation with that. But in our case, we are using a robot in a simulated environment, trying to learn where it's going in a maze. We want this to be robust. Robustness is a machine learning system, and a machine learning system refers to the system's ability to perform reliably and maintain high performance. So we're going to add some noise to it to see how it handles this, and yeah, that's what we're going to be doing. Okay, starting off strong. What is SLAM? SLAM stands for simultaneous localization and mapping. And it's pretty much as an entity moves within an environment, it's mapping and figuring out what's within its environment, and also figuring out where it is within the environment as well. So it's mapping itself and mapping the environment. That's generally a SLAM problem. So our robot is going to move with simultaneous localization and mapping. What are some real-world applications? So for biomedical healthcare, we could be assisting medical professionals with this kind of thing, enhancing diagnostic capabilities, performing surgeries. You can see there, the first thing that comes to my mind for this kind of thing is self-driving cars, being able to drive on roads and not hitting trees, driving and making with some uncertainty that this is a good turn to take. Search and rescue. Under adaptive optimal control, we want to look at the robot's dynamics and external forces. And some optimal control strategy. Okay, what's our method? What are we doing that's new? So this is a lot of words, and I'm going to break it down in the later slides. But we want to integrate Bayesian theory and vision transformers into reinforcement learning, which is known as Actor-Critic, to measure the uncertainty of the predicted action, essentially. And we're going to be doing this within the SLAM problem that I mentioned earlier. So that's kind of our main broad method and focus. So let me break down what reinforcement learning is. So to explain this well, I'm going to use an analogy like a kid trying to ride a bike. So our kid is riding a bike, right? And maybe he turns a little bit too aggressively to the right and he falls and skins his knee. Right there, he gets a negative reward through the skinned knee. Maybe I shouldn't have made that turn. So he backs up and starts doing it again. And instead of turning really aggressively right that he did to result in a skinned knee, he keeps going. Dopamine rush. He's still on the bike. There's your positive reward. And so through trial and error, this kid is learning how to ride a bike. So in our case, through trial and error of a robot hitting a wall or not hitting a wall, it's getting a reward, it's getting penalized as well for bad mistakes that it makes, and it's learning how to navigate in that environment. So you can see right there, RL framework, the agent interacts with the environment gives it feedback, and the agent receives a reward and keeps going, keeps making decisions. So in reinforcement learning, a policy refers to the strategy an agent uses to decide its actions, and policy-based learning focuses directly on learning this policy, mapping states to actions in a way that maximizes the total reward. On the other hand, a value represents the expected cumulative reward that an agent can obtain from a given state or state-action pair. Value-based learning aims to estimate these values, guiding the agent to choose actions that lead to the highest reward. So in the Actor-Critic method, it combines these two. The actor network predicts what action the agents should take, and it learns a policy that directly maps states to actions, and it serves as the decision maker for the agent. The critic network, on the other hand, evaluates the actions taken by the actor. It learns a value function that estimates the expected cumulative rewards for state action pairs. So those are the two main parts of this reinforcement learning algorithm. So in our method, the actor is a convolutional neural network, and the critic is kind of the meat of this whole operation. It's a Bayesian vision transformer. So I'm just going to quickly gloss over what a CNN is, convolutional neural network, but it's not the focus of this. A CNN is a type of deep learning model, particularly well suited for processing and understanding visual data. They're designed to automatically and adaptively learn from spatial hierarchies of features and through the use of layers that perform convolutions. They scan the input data with filters, they capture important patterns. CNNs are widely used for image classification, object detection type of tasks. But like I said, the critic is the meat of this whole thing. So in our critic framework, which I mentioned was a Bayesian vision transformer, it's centered around Bayes' theorem, which you can see right there, which enables the updating of prior beliefs about model parameters as new data becomes available. So it's basically, instead of it just being a deterministic, a fixed data point, we have a distribution, a probability distribution of what an action is, of what kind of thing you could do, pretty much. So in this, P of A given B is the posterior, representing the updated belief about the parameters given the observed data. P of B given A is the likelihood, describing the probability of observing the data under the current parameters. P of A is the prior distribution, representing initial beliefs about any parameters before observing any data. P of B, lastly, is the marginal likelihood or evidence, a normalization constant ensuring that P of A given B is a valid probability distribution. Now, a quick side note, the normalization constant, or P of B, is just too large to quantify. It's just too computationally heavy, so there's a couple of approximation techniques, and the one that we're using is variational inference, which is just kind of saying it's a Gaussian, we don't have to worry too much more about it. So we're just smacking a normal distribution on it and calling it a day. The other one's Monte Carlo, Markov case Monte Carlo, and that basically takes or samples from the distribution, but we're using variational inference. So Bayesian theory plus the vision transformer. Vision transformers use patch-based input processing, which divides an image into smaller patches, flattens each patch, and linearly embeds them. These are treated as tokens, similar to words in a sentence for natural language processing. It's got a self-attention mechanism, which is a key component in transformer architectures that allow the model to focus on different parts of an input sequence without producing an output. It weighs the relevance of each element in a sequence relative to the others, enabling the model to capture relationships effectively. So this is happening to weigh the importance of each patch in relation to the others. So this allows it to capture global dependencies and context across the entire image. So positional encoding also happens because transformers don't inherently understand the spatial structure of an image. Positional encodings are added to the patch embeddings to retain information about their original positions in the image. Lastly, in a vision transformer, there's a lot of layers. They consist of multiple transformer blocks, each containing layers of multi-head self-attention and feed-forward neural networks. These layers help the model learn complex patterns and relationships across the entire image for accurate classification or other vision tasks. So as a whole, I know it was a lot of words, the Bayes theory is giving uncertainty to our actions, and the vision transformer is helping us to effectively process all of this image data that's coming in from a robot in a simulated environment. So they're working together. So what are we using? We are using OpenAI, Jim Gazebo. It's a open source library. We're using this in Linux. And these are all tools used to simulate the environment that the robot will be operating in. So that's generally what we're using. And thank you, NSF, for supporting this work. And thanks for listening to our presentation. Feel free to contact me or any of us. Our emails are right there. Yeah, and they're all our references. Thank you.